Welcome back to part 2 of week 6, the spontaneity of a reaction, where we're looking at whether a reaction is spontaneous or non-spontaneous, whether it happens on its own or requires some energy to happen. So we're kind of looking at this different reaction, and we looked at that Gibbs free energy equation last time. We were solving for the triangle of G, which is change of G. And so we were looking at whether or not, what temperature, which is a really important point when we're looking at this, to determine whether or not it's going to spontaneous, happening on its own, or non-spontaneous. So down here you have a little interactive opportunity in which it has you play around. So it says at what temperatures will the change of G be greater than 0. So if I guessed, I don't know, let's click 473. It says then you can drag them in here. Oh, non-spontaneous. You're going to kind of work and guess around. Maybe a higher temperature will cause it to happen on its own. So if I click 873, put those in there. Non-spontaneous again. Let's see. Oh, there it is. So spontaneous was at 1073 Kelvin. Remember, when we talk about Kelvin, Kelvin's a positive number, temperature, so that is why we use Kelvin. We need it to be a positive. Okay, so when I'm looking at the temperature really determines if reactions are spontaneous or not. We saw that at high temperatures, that last one, the reaction is spontaneous. It happened on its own, and that's because we want this change of G, this Gibbs free energy, to be negative, okay? And it's only negative for that reaction if the temperature is very high. Reactions that absorb heat are endothermic. They lead to increase in randomness, like ice melting, will only be spontaneous at higher temperatures. Because they require energy to come in, you need a lot of that energy. And that energy is often coming from that high temperature. Okay? So like ice freezing, they release that heat. They don't need that much heat. Remember, heat, temperature, kind of similar. That energy, they're spontaneous at lower temperatures. So they don't need that heat from the temperature. So they're going to happen on their own at lower temperatures, okay? Now, we're going to look more just to calculating the Gibbs free energy, which we can just plug in numbers and solve for it, okay? So with this one, it shows us an example. We have from liquid water to solid ice. We know it's exothermic with a negative enthalpy, and it also has a negative entropy, okay? So the negative enthalpy right there and negative entropy. Okay, we can plug those value in. At 25 degrees Celsius, we just add 273 to convert it to Kelvin, so the end total is going to be 298 Kelvin. Okay, so we can plug that in. We can do the change of H, which is that one right here. So change of H goes first. Okay, then we can put in the temperature, times it by the negative 22.1, and we can get this total right there. At the end, it is positive. So we know when Gibbs free energy is positive, it is non-spontaneous at 25 degrees Celsius. Okay? And so we know that ice doesn't freeze spontaneously at room temperature. I mean, we know that, but this is the scientific way and the proof that it's not going to happen because we get a positive value when we plug in 25 degrees Celsius. Okay? Which is kind of like a room temperature almost, or a little bit warmer. Okay, so let's practice a little bit with plugging this in. So we have this formula, and they're going to give us a different temperature. Okay, so instead of 25 degrees Celsius, this time we have 15. Okay, so we're going to do the same thing. We're going to plug it into this formula, and we're going to kind of solve it out. Now, I pulled up kind of a whiteboard app. Excuse my, handwriting. I was trying to type it, or not type it, but write it with my mouse. So what I did, I plugged it all in. You took the same change of H, subtracting that temperature times the negative 22.1, which was the change of F. Okay, again, I had to solve for temperature. I'm doing 15 degrees now. I'm adding 273. Okay, so my total temperature for Kelvin, I should, write it into Kelvin, is 228. I plug that 288, okay, in over here, so that I can just negative 6,030 minus the multiplication of these two things, so 288 times the negative 222.1. Okay, that's that value right there. So a negative minus another negative in the end, I got, I just changed this value to a plus, get the total of 334.8. See if that's one of my options. We cross our fingers that it always is. Oh, it is. Okay. Check it. Great. Okay. Now, is this a spontaneous at this temperature? And a lot of times I like to remember the whole idea, and I wrote this down on my notes, is that when it's negative, it would be spontaneous. If it's positive, it's non-spontaneous. So you need to kind of remember the difference between those two things. Well, we got a positive number, so meaning that it's going to be non-spontaneous. So is that reaction spontaneous? No. It's correct. Now, if we did this again, and you can have it to plug into that same formula, okay, for negative 10 degrees Celsius, okay, once you plug that in again, you're going to figure it out. You got to add the 273 plus that to get the Kelvin, plug in those numbers again, so do the same thing of what we did over here, but this time you're going to have the negative 10 over here to plug that number in over on that side, okay? So try that. I'm not going to do that with you, but try it. It's not so bad, okay? But in the end, you should get a negative 217, and it's one of those options. Is it going to spontaneous or non-spontaneous? Well, it's negative this time. It's going to be spontaneous. Okay, negative 10 degrees, that's below freezing, so we do know that ice does freeze at this temperature, okay? So we can solve for the temperature, though. If we want to know what is that temperature in which it becomes spontaneous, so we don't just sit there and guess, okay, we can find out if we set this Gibbs free energy, the change of G, into 0, equaling 0. So we start with that same equation. We substitute values for H and set the G equal to 0. So you're solving for T. So we put 0 on this side. We put the negative 6,030 over here minus T. We're leaving that there because that's what we want to solve. That's the variable we want to solve for. And then we're putting negative 22.1 in for the change of S. Okay, we rearranged to solve for T. In the end, it's 273, which is 0 degrees Celsius. We know that's the freezing point of water. So we kind of knew that going in, but this is the way they're kind of showing you and proof that at 0 degrees Celsius is that point where the reaction becomes spontaneous. Water is going to freeze at anything below 0 on its own, and it's not going to when the temperature is higher than that. Makes sense. Okay. So we have a few more questions to kind of look at and plug in some numbers. Okay. So we want to figure out that they have the same sign, and so that means that it really depends on the temperature. It's not going to automatically be spontaneous or not when we first looked at that, what was going on in the last time. So which one follows describes if we have a 298, okay, if we plug it into that formula again, so we have a temperature, we don't have to go, it's already in Kelvin, so we can figure this out. So if I plug this in, so let's solve for this first. So 298 times, what is the change of S? Negative 76.6. Okay, so we get that number. And then we have to subtract. So we take that number, 52,626.8. We're kind of subtracting it from this one, so 580 minus 52,626.8. So we have about this number. We can round it a little bit, and it will be negative, and it is spontaneous. Okay. Now, which describes the reaction above. We're at the point where it's not always, it's always or never. It's not really going to be an option, because if we go back to this, which was I screenshotted this from the beginning part of the lesson. If we have both of them being negative, it depends on temperature. It's never going to be always. Remember, this was the only, way that we could really have it always or never. When the signs were both the same, it really depended on temperature. Okay, so since they're both negative, well, it's not going to be always or never. It's either going to be spontaneous at high temperatures or spontaneous at low temperatures. Well, it's going to be spontaneous at low temperatures. Okay. And then we have a little bit, if we plugged this in, if it's high enough, the temperature, we need a very high temperature for it to be non-spontaneous. Okay. So this we kind of look at that what can happen is that we can have what the conversion, they're saying the conversion of diamond to graphite is spontaneous. It does happen on its own because it is a negative value. But it does not mean it happens quickly. I mean, your diamonds aren't going to just, change to graphite like the picture is happening. It's incredibly slow, and we won't even notice it's ever happening. But it would eventually happen, but not in a time we would ever see it in front of us. Okay. So we can talk about there's an equilibrium. So we didn't talk about this as much in class, but the arrow in a reaction can go both ways. And so that you can kind of go forward and backwards of a reaction. It's not always one way. I know in class we've often drawn it in one way, and that in our class that was good enough for us. But the forward reaction can be spontaneous. So then that means the other reaction can go like the opposite or different way, reverse it. And so it's just kind of interesting what's going on with that. I'm going to kind of move forward because we're got a little bit of time. So, and also the last little thing is we have a cell, a galvanic cell. It's a spontaneous redout reaction. So if it's spontaneous, then we do need to know that E is less than, it's E because G is a negative number, meaning it's spontaneous, so it has to be negative. Okay, we don't really know enough about anything else to really be determine their sign. Okay, so in the end, okay, there's a few more questions to answer with this. And so spontaneity depends on temperature because they're both positives. Going back to our thing, we don't know if that's always spontaneous or negative or never spontaneous. We have to depend on temperature. If we plug them in, so again, the 300 Kelvin gets plugged in for temperature. We have the H right here. You just plug it all in, subtract, kind of that sort of thing. Your answer should be, the answer should be 229. Okay. Now, is it positive or negative? That comes back to what's going on. It is going to be non-spontaneous because it's positive. Okay. And then at what temperature does it become spontaneous? And we are going, it needs to be a high temperature. That'll give you a negative number. Okay, because you'd be subtracting a high number. Okay, so that's kind of the end of this. You will be taking the quiz after this. This is the end of the lesson for this one. It's also the end of the unit. So you have just this quiz to take, but you also have the practice. I know mine says a green check because I clicked on it. You do get a grade in the grade book if you submit it to your mentor teacher. It is just kind of going through everything you've learned throughout this whole kind of unit. This is the end of the unit that we're going to be doing, so it's just kind of some answer. Just kind of working through a lot of just answering in your own words some questions, some bullet points, okay? So if you have questions on that, ask me. But then we get to go into nuclear chemistry, which is kind of fun right after this for next week. So, as always, if you have questions, ask. If not, hope you have a good week.